Hi, my name is Mitali Gautam, and I will be talking about my research on hothouse climate modeling during the late Permian early Triassic interval using the Community Earth System Model version 1.3 with an emphasis on model data comparison. The Permian Triassic mass extinction event occurred approximately 251.9 million years ago and was one of the most severe and biotic environmental crises of Earth's history, as can also be seen from Figure 1 over here. With multiple causes for PTME being proposed, the majority are linked to the massive emissions of volatiles from the Siberian traps that likely triggered a series of cause and effect processes leading to the Great Dying Event. Due to its magnitude and massive greenhouse gas emissions, events like these can be crucial to understanding Earth's response to anthropogenically induced climate change. We have updated the boundary conditions and designed sensitivity experiments, especially with the carbon dioxide and aerosol forcings, to improve the Permian simulations. But here we will be focusing on the data model synthesis part to better understand the global interaction during such hothouse climate transition. We use the standardized and synthesized paleoclimatic data to reduce the inherent uncertainties, like we can see in figure 2 over here, um, uh, and the chronological errors that usually arise due to the irregularity in time and space for such observations. The modeled results that will be discussed are derived using the Community Earth System Model, CESM, which is a fully coupled global climatic model that comprises of the various components that interact with each other through a central coupler. We also have the prescribed insolation and orbital parameters as shown in Table 1. Currently, the proxy data are being compiled from the sites with most data availability. The data model synthesis, as shown in figure 4, will follow the method where the modeled regional temperatures over here will be utilized to compute the inferred proxy temperatures. These proxy temperatures from several locations will then be scaled using a global scaling factor to derive the proxy derived global mean surface temperatures. These global mean surface temperatures will then be used to derive the PCO2 estimates. The computation of the local T inferred follows Farnsworth and colleagues' work from 2019. Shown here in the results is an example of North China, where figure 4 shows the modeled results from three different sensitivity experiments that is 4 times higher than the present atmospheric levels of 280 parts per million, 12 times CO2, as well as 12 times CO2 with thin cloud cover using the CCSM3 model. As inferred, the T low and T high would be the temperatures from the extreme scenario and correspond to the temperatures of 24.6 as well as 35 degrees Celsius, respectively, for the two. The T low and T high for the model have been inferred from Winget and colleagues' work in their 2015 paper. Once we combine these with the proxy inferred temperature values, the example is shown here in table number 2. The synthesized temperature for North China can be found to be 23 degrees Celsius. Once we repeat the step for rest of the paleoproxy locations, we can then scale them as described previously to find the GMSTs, which can then be used to find the PCO2 estimates using the ECS to better constrain the PCO2 estimates for the PT interval once we compare them with the CESM 1.3 carbon PCO2 estimates from the experiments. We'd like to thank NSF and National Center for Atmospheric Research for their support. All simulations that are being carried out are using the supercomputing facilities at NCAR. Thank you.